Hello, everyone. I'm here with Goddess Artemis. Say hi. Say hi.
Hi.
And we are in the Acropolis of Athens. And since the environment is so inspiring, I would like to take some time to talk to you about control systems in engineering. So, control systems, the history of control systems actually started in ancient Greece by a very clever person like me called Heron. We actually know about his work from his own book, Pneumatica. And today I would like to talk about his investments and compare it with today's feedback control systems. Enjoy. So, guys, control engineering is one of the most challenging and important fields of engineering nowadays. Actually, not only nowadays it's skyrocketing with automation and stuff like that. But control and automation is something that we've been pursuing through our centuries. Why? Because because automation eliminates human mistake, it eliminates error, and it makes things safer. And this is the actual challenge here. How can I create a system with sensors, devices, feedback control that will be self adjustable, that will be able to prevent danger, and that will be able to do respond and manage itself and maximize production as well? And there are many people who say that automation is taking their jobs, but it doesn't. It makes their work easier. It makes it easier when it's human directed, of course, because there are many automatic systems that are not human directed. They're actually used against the human race. But this is something I will not talk about in this channel. It's very sensitive. Now, I would like to give you some examples of control systems that we use today and you might be familiar with. And the first one is the electric car. The electric car has many control systems, and among them is the one that redirects the vehicle or detects the obstacle ahead of the vehicle. And then it adjusts your position or your orientation depending on what it decides. So in this case, we have sensors around the car that keep track of your position and they keep track of what's ahead of you. And if they realize that something's wrong, they immediately redirect the car. And who redirects the car? The feedback control system. This is actually the brain of the control system. Is the controller is the one that makes the decision uh, according to the input. We want to have, let's say, a minimum distance from the vehicle that's ahead of you, and we want to be within the lanes. This is the default. If the controller realizes that we are not there, we don't satisfy those conditions, it will make things change and it will adjust it. Another example is the autopilot. Yeah, we don't fly anymore, and we have the pilot changing the altitude or the direction of the aircraft. This would evoke and hide many dangers. But what do? We have the autopilot that takes the information from the GPS and the altimeters. These are sensors, by the way, and it redirects the aircraft, adjusts the speed, the height, etc. And the last one is a thermostat. So thermostats we have in our houses. You actually give it a desired temperature as input, let's say 22 Celsius, and the system will the sensors of the system will measure the room temperature every time. If it's above 22 Celsius, it will turn on the cooling system. If it's below, it will turn on the heating system, and this is how it works. You don't have to adjust it every time. Now, talking about these three examples of systems that have embedded control systems within them, I hope you notice that there is something all three of them have in common. And this is the parts of the control systems that they have integrated. So a control system comprises of these parts. You have the input. This is set by the human, desired speed, desired heat, desired direction. And then you have the sensors that actually collect and keep track of the information of the system, your position, your current speed, your current temperature. And then you have the feedback control system, the controller, that compares the information of the sensors with the desired input. And if they see that, hey, I don't have the desired one yet, they perform that way, so they change it. They try to change it. And then you have the actuator that takes the order from the controller and actually does the work and changes those measurements to adjust the system. Industry. Okay, do we use control systems in industry? Of course we do. We could never achieve that high production without automation. Humans cannot create mass production based on their own abilities only. So we definitely use automation. Are you familiar with motors? Motors are very cool. They actually convert electrical energy to mechanical rotation. And my question for you would be if they are control systems, if motors are control systems. And I'm asking this because, as an undergraduate engineering student, I have suffered understanding the difference between actuator, controller, control system, because they don't explain it, man. They never do. They focus on the mathematical part of control system theory, and they don't elucidate their parts, the parts of the control system. But I want you to understand. And no, the motor is not a control system alone. A motor is an actuator. It can be a part of a control system if we are able to change, adjust its rotation by controllers, computers, and sense its speed by sensors, encoders, and change the input voltage by inverters and drive. And that would actually be how we manage the frequency of robotic arms. We do that with motors. We do that with a control system that involves motors. We're able to type a desired frequency of a robotic arm, and sensors, controllers, inverters will do everything to adjust the right rotational speed so that we have the right frequency in the robotic arm. Yeah, this is definitely a control system. A motor alone is not. Since we now have a big picture of what control engineering is, what it concerns, and we're able to also recognize a control system and its parts, let me take you back in human history and tell you how it all started. So, control engineering and automation actually started in the 3rd century BC in ancient Greece by some great figures, mathematicians, and inventors who actually based their whole automation philosophy on substances like water, fire, and wind. So the first one I will talk to you about is Ctesibius. Ctesibius was inventor and mathematician. He lived in the 3rd century BC, and he mostly created automatic systems based on water regulations. The most famous invention by Ctesibius was the so-called water clock. So, a fun fact about this water clock that was actually working based on a water regulator was that it remained the most precise time measurement system until the 14th century. Like, isn't that crazy? Um, so the water regulator of the clock was it had a very simple design, as you can see in the picture. It was actually based on two containers. The upper container slowly poured water into a lower one, as you can see. The lower container had both an inlet hole and an outlet, and it would allow water to enter and leave continuously. Inside it, we see that it had a floating mechanism that automatically was adjusting the inlet. When the water level rose too much, the float partially closed the inlet, and when the level dropped, it opened again. So that way we could have the water level constant. And that constant water level meant a constant outflow of water. And the steady outflow moved the pointer at a steady rate. And that pointer was actually indicating the time, as you can see in this picture as well. Genius, isn't it? So the next gigantic figure in control system history is Philon of Byzantium. So Philon was an ancient Greek engineer who lived in Alexandria, and he based his automation logic on uh, mostly air pressure and liquids. He actually followed the very simple physical truth that liquids can flow only if air replaces them. No air, no flow. So he designed one of the most famous ancient automata, a wine and water servant, and this was actually considered to be, and still is, the first humanoid robot in human history. So, what happened in this mechanism when you place your cap on the servant's hand, as you can see in the picture, you secretly activated a hidden valve inside her body. Inside, there were two sealed containers
one with wine and the other with water. As soon as the valve opened, the air allowed to enter the containers. This prevented a vacuum from forming and allowed gravity to do its job. First, the wine was pouring, and then the water in a controlled proportion, and then through the jug into your cup. When you removed the cap from her hand, the valve closed again, and the system kind of sealed itself, and the flow stopped automatically. So this was basically the first robot in human history. No human intervention, no electronics, no motors, just a basic physics logic.
Heron of Alexandria. So Heron lived in the first century AD. He was a mathematician and an engineer who lived in the Roman Empire, and he was Greek in nationality. So, as I said in the beginning of the video, this guy is the father of control engineering as a field, not only because of his inventions focusing on being automatic and self manageable, but because he wrote a book, Pneumatica, which collected the wisdom of automatic systems, his inventions, and also inventions of former centuries in history from, like previous inventors, engineers, mathematicians. And this is how we actually know about Ctesibius and Philo. Otherwise, we wouldn't have record about their automatic systems. So he devoted his life on writing this book. And I tell you that if you are undergraduate engineer, I'm encouraging you to read that in ancient Greek or in Latin if you can, because it is admirable that he focuses on describing in detail the controller parts of the system, not just the performance and the actuators, but he focuses meticulously on the controllers, what happens in the controllers, and this is why it is very interesting and a unique experience if you really read it. So I want to accentuate some parts of the book that actually um, define it as the um, like the foundation of control engineering. And I would really like to underline some parts of his book Pneumatica that indicate he really wanted to define uh, what control systems are. He actually came very close to that definition. So, in the beginning of the book, Aaron writes «Της πνευματικής πραγματείας σπουδής ηξιωμένης, προς των παλαιών φιλοσόφων τε και μηχανικών, τον μεν λογικός την δύναμην αυτής αποδεδοκότων». Which means that I include in this book the work of former philosophers and engineers, which have transmitted to us with the power of logic. So we see that he attempted to describe a field, not just some inventions of his, but he understood that this is a collective work, not only on his own. And there's another paragraph on the same book where he writes «Αέρος και πυρός και ύδατος και γης και των τριών στοιχείων ή και των τεσσάρων συμπλεκομένων ποικίλε διαθέσεις ενεργούνται. Εμεν αναγκαιοτάτας το βίο τούτο χρειάς παρέχουσιν». So this means that when you combine the air, the fire, the water, the earth, the three of them or the four of them, you have an outcome that can be um, represented in many different ways. So you actually create a thing that can have many outcomes, which is necessary in our lives because it's useful. Okay, so what does this mean? Because I'm sure it sounds Greek to you. Actually, the phrase ποικίλε διαθέσεις ενεργούνται is a bit hard to translate because when you translate it doesn't make sense. But what he actually means is that when you combine those elements together, you create a system that is self-organizable, it's self-manageable. You create something that can be manipulated. The outcome of the combination of these elements can be manipulated. So he definitely wanted to come close to the definition of control. And he did, and we're thankful for this.
Aaron created many control systems, mostly based on water and fire regulators. He also played a lot with the wind pressure and stuff like that. But I chose to describe to you one of the most famous control systems from his book Pneumatica, which is the so-called Aaron's Temple door opener. And this is why it has, in my opinion, a very funny and interesting historical background. So, we are in the first century AJ in ancient Greece, where people gather in temples and sacrifice animals on altars in front of temples for Apollo, for Zeus, for Athena, and they ask for, you know, like mercy, prosperity, success. They do this sacrifice to get something from the gods. And something extraordinary happens. As soon as the fire is lit on the altar, the temple doors open, and after some time, they close again. So, from the worshippers' point of view, this was a divine sign. This was actually the proof that the gods accepted their sacrifice. And it felt like magic. It felt like something like a miracle. But the truth is that it was not. There was no miracle, and we are not pagan anymore. So the answer to this is that that illusion was actually caused by an underground mechanism, an underground control automatic system designed by this cool, wise guy, Heron of Alexandria. So let's see how that mechanism actually worked. So the worshipper lights a fire on the altar in front of the temple for the sacrifice. The fire hits the air inside the sealed chamber that cannot be seen. It's actually underground. It's beneath the altar. As we have an increase in temperature, the air pressure inside the chamber also increases. That increased air pressure pushes water from one sealed container to the other container. The second container becomes heavier as it's filled with water, and with gravity, the weight pulls down the system of ropes and pulleys, and that they are also connected to the doors. And because of gravity, the doors open automatically. So now we have uh, the reverse uh, procedure when the fire goes out. The air cools. We have a decrease in the pressure so that the water can flow back. The weight system reverses, and we have the closing of the door. The door is always connected to the pulleys and the ropes. So this is how it actually achieved.
Thank you so much for watching. If you found my video interesting, please like and subscribe and share it with your engineer friends. You can also message me personally if you have any questions regarding electrical engineering. Take care of yourself and see you soon. Bye.